Hello, my name is Lucas Contreras. I'm part of the senior design team for our linear transformer driver for spring 2022. My fellow team members are David Martinez and Austin Davis. I'll be running through each part of the design and showing you how our design works. So starting from here, ours is fundamentally a transformer, so that has a primary and secondary side. That is all due to windings around a magnetic core. Whenever you send current around those windings, it induces a magnetic flux through the core and then induces on the secondary side the secondary current, and then representing the voltage on the secondary side as well. Ours is ideally going to be a 1-to-1 ratio, so we're hoping to get the mutual inductances as accurate and the windings accurate enough to produce a 1-to-1 transformer. On this picture, you can see how this is going to be a disc design, and then from the PCB, it's going to send the current around our core that's going to sit in between a top layer and a bottom layer to create that winding, and then have multiple circuits around that to act as each of those windings. It's not going to be a continuous winding, they're all individual windings, and I'll explain what each of those circuits are in a bit. So you'll see that the current will induce that current and the secondary current, and then produce that current across our load in the end. Our requirements for this semester to meet would be a output of 30 to 50,000 volts at about 500 to 1,000 amps through our secondary side. So how this works, we have multiple circuits here. So from the beginning, we're going to be sending a signal from a transmitter to send a signal to a receiver that's going to be on our board. That's going to activate our windings. Those circuits I mentioned before will consist of a capacitor, a MOSFET, and a driver IC. Basically what's going to happen, we are going to charge 20 total capacitors, not individually, all together on the board, and then have their holding charge on the board be activated through the MOSFET switch. It's a low side driver, which means we're going to apply 15 volts to the gates of the MOSFET and then open the circuits to allow that current to flow through our primary side of our transformer. Okay, so going from here, this was our test circuit to produce similar circuits on here, ideally, but this is the final design. So like I mentioned, we are following, just the windings of a transformer. So each of these are the individual 20 MOSFET circuits around the core, completed here. So this is our magnetic core, and then the current is going to flow away from the middle, around, and then back looping around our core. So our induced current, as opposed to the picture I showed, it's going to actually flow down in the end. So like I said, we have our receiver circuit here. They're all individually powered by one power source, but with regulators, we're maintaining the voltage needed for the receiver. There is also a 15 volt regulator for each IC, because their outputs are dependent on what their supplying voltage is. So those are set to 15 volts. And then from here, we have one main gate driver to send one signal to all of the other gate drivers. So here's the completed setup. Here's that top layer that's going to complete our circuit. And then what we're going to do, we're going to charge the capacitors to 20 volts. Here I'm turning on the transmitter circuit that's going to send our signal to the board. And then we're going to charge this to 20 volts by sending the signal from the receiver. It's going to go in here to the receiver, and then also the board's power source right here. You can see that it's indicated on. It's very bright, so we put this cap on it. We're going to charge this now and then run it through the oscilloscope. We should see at a 50% duty cycle for 100 kilohertz, you'll see about a 5 microsecond length pulse. So just reset that. We're going to charge. That's the initial charging backlash there. Set it, and then we're going to trigger, and we get our pulse. That lasts for about 5 microseconds. Each indication is 1 microsecond, so that is equivalent to what we expected.